This video will just be the wrap-up of a problem that we started previously. It's 2010 Form B Problem 4, non-calculator question, and Parts A and B were done in a separate video, and in Part C here we're asked to find the total distance the squirrel travels during the time interval from 0 to 18. Now in Part B what we figured out was that the squirrel traveled 140 units in the positive direction from this t-value 0 to this t-value 9. And then across the next 6 seconds, 6 minutes, whatever the units of t are, the squirrel traveled in the negative direction because of the negative velocity, so it traveled back toward its starting point. And we were able to find the area of this trapezoid right here and determine that it traveled 50 feet or 50 units back toward its starting point. And then on the last little piece of the graph from 15 for t to 18 for t, the squirrel traveled 25 units, and this was back in the positive direction as indicated by the graph of velocity being above the x-axis, above the t-axis, or positive. So if we want to figure out the total distance the squirrel travels, well, it travels 140 feet in the positive direction across this time frame, travels 50 feet in the negative direction across this time frame, and it travels 25 feet in the positive direction across the last 3 units of time. So the total distance traveled is going to be 140 plus the 50 plus the 25. And so if you sum those, what you end up with is 190 plus 25 more. So I think you end up with 215. So when we were considering position, we had to recognize which direction the motion was happening in. And on this piece in Part B, we had to subtract the 50 off of the 140. But in the case of total distance, the squirrel is constantly moving back and forth on the wire between the buildings, so we just find the area between the curve, the velocity curve, and the t-axis on each interval, add all those areas up, and we have our total distance traveled. In Part D, it wants us to take a piece of this velocity graph, the portion from 7 to 10, and do a little bit of work with it. So on the interval from t equals 7 to t equals 10, or I guess I shouldn't say equal, it would be the t values between 7 and 10, since we're not allowed to be equal to the endpoints here. But on this piece of the graph, this negatively sloped line that we see here, what we're asked to do is we're asked to come up with an expression for the squirrel's acceleration, an expression for the squirrel's velocity, and then also an expression for the distance traveled at t seconds after or t units after the beginning of that time frame. So if we think about what we're looking at a graph of velocity. And so to find the expression for v on this interval, all we're going to need is the equation of this line. So to find the equation of this line, and that's, wow, a horrible attempt to trace the line, but to find the equation of that line, that's just, an algebra problem. You have the endpoints or 2 points that are on the line, so to find the slope of the line, you're just going ahead and going to do difference in y values, so I'm going to do 20 minus negative 10 over the corresponding difference in x values, so the x value here would be 7, and then minus the x value here, which would be 10. And so if you simplify that, you're looking at 30 in the top and negative 3 in the bottom, so the slope of that line is going to have to be negative 10. And if we want the equation of the line, we're going to have to go ahead and either use slope-intercept form or point-slope form. If I start with point-slope form, I'm going to have y minus, I like the coordinates here where both pieces are positive, so I'm going to have y minus y1 first, which is 20, and then that's going to be equal to xm, which we got negative 10 for, times the quantity x minus x1. So x minus x1 would be 7. Now we do want to kind of clean this up a little bit. That is the equation of this line, but what we want is to kind of change the variables a little bit. We want a formula v of t, and we could solve this for y simply by adding 20 to that side. What I'm going to do is I'm going to change the y to a v of t. Right? The equation of this line is basically what graphs v of t, which is sitting in front of us, from this point down to this point. So v of t is going to be equal to negative 10 times the quantity. I'm going to change that x to a t, right? I wouldn't want to call my function v of t and then put an x over here. So I'm going to change the independent variable to a t from an x. And then I'm going to have to add 20. So there's an expression for velocity. We want an expression for acceleration, and we've actually already determined that if you think about it. The acceleration relative to velocity is going to be the derivative of velocity. So the derivative of this straight line is going to be the slope of the line. And we found the slope of the line. No matter where you look on that line segment, the slope of the tangent line is -10. So the acceleration function is going to be -10. So here's a velocity function, here's an acceleration function. The last thing we're asked to determine is we're asked to determine a distance formula. So if we go ahead and try to determine a distance formula, this is going to be a little bit tricky, but I'm going to start with my velocity. Okay, I'm going to come back over here so I have enough room across the bottom of the screen here to fit it in. So I'm going to start with my velocity function, and I'm going to simplify it a little bit. I'm going to distribute into my set of parentheses in this velocity function, so I'm going to write it as -10t plus 70, and then plus the additional 20. So I guess that's going to really be equivalent to -10t plus 90. If this is velocity and I want to work backwards to a position function, what I'm going to have to do is I'm going to have to figure out how to undo the derivative, right? To go from velocity back to position, I need to do an antiderivative. And so my position function, x of t, is going to be equivalent to the integral of v of t with respect to t. And so if we do the integral of this expression, remember there is actually a t to the 0 that we can tack onto that plus 90. If we integrate this expression right here, we're looking at the -10, which is a constant being copied into our antiderivative, add 1 to the exponent on the t, divide by the new exponent, copy the 90, the constant, into your antiderivative, add 1 to this exponent, so it becomes a t to the first, divide by 1. You don't have to show the first power, you don't have to show the division by 1. It is an antiderivative, and what we always pick up when we do an antiderivative is a constant of integration c. Now if we clean this up a little bit, the -10 over the 2 is really just a -5 t squared, and then we have a plus 90t. We don't know what c is. Now, if we knew something about the position at a certain time here, we'd be able to solve for c. I think what we can actually do is we can figure out the position of the squirrel at t equals 7. The position of the squirrel at t equals 7 is going to be the area of this trapezoid right here. So if we can find the area of this trapezoid, that's going to be the position of the squirrel on the wire between building A and building B at t equals 7. So what is that position? Well, using the formula for the area of a trapezoid, we have this parallel side measuring, what, from 2 to 7 for the x value, so that would measure 5 units across. And then across the bottom, the other parallel side would be 7 units. So the area of this trapezoid is going to be the average of the parallel sides, the average of the bases, times the distance between the bases. Well, the distance from this base to this base is going to be 20 units. So if you think about it, this is 12 divided by 2, that's 6 times 20. So the position at 7 is going to be 120 feet, right? 6 times 20, 120 feet, 120 units from its starting point. So basically what I know is that at 7, my position function has a value of 120. So if I wanted to go ahead and use this information to solve for c, what I'd be able to do, and let me scroll down to get a little bit of extra space at the bottom here, what I could go ahead and do is I could say since 7, 120 has to be on the position graph, I could go ahead and I could put 7 in for t, (120) in for the position at that time, and we can solve this for this constant of integration c. So this is going to take a little bit of time, right? You have to do some arithmetic here. You're going to have to figure out what -5 times 49 is. And then you're going to have to do, let's see, 90 times 7 should be 63 with a 0 tacked on at the end. So you have a little bit of arithmetic that you have to take the time to do. I'm not going to really waste your time and do all of that arithmetic. But to wrap this up, what you end up with here is negative 245 for this product, add on 630, and that's going to give you positive 385 plus C equals 120. Well, to solve for C, subtract 385, and what you get for your constant is you get negative 265. And so, again, without a calculator, it's a little bit of a pain to do the arithmetic there. We kind of cut to the chase and just kind of provided some of the solutions here. But your position at any time between t equals 7 and t equals 10, given by x of t, is going to be exactly what we had here. So negative 5t squared plus 90t, and then plus the constant we found, which was negative 265. So I'm just going to write in minus 265.